On July 4th, in the year 1054, a new star appeared in the sky. It was so violently bright that Chinese astronomers recorded it being visible in broad daylight for almost a month. What they were witnessing was the explosive death of a massive star, 6,500 light-years away. Today, the shattered remains of that explosion form the beautiful, chaotic cloud of gas we call the Crab Nebula. But hiding deep inside that glowing cloud is a corpse, a dead star crushed down to the size of a small city, spinning 30 times every single second, commanding a magnetic field a trillion times stronger than Earth's. Today, we are taking a deep dive into one of the most extreme, terrifying, and fascinating objects in the known universe, the Crab Pulsar. But how does a dying star transform into a cosmic engine so powerful that it can light up an entire nebula? To understand the Crab Pulsar, you first have to understand the sheer violence of its birth. When a star at least 8 times the mass of our Sun runs out of fuel, its core can no longer support the crushing weight of its own gravity. In a fraction of a second, the core collapses inward. The pressure is so incomprehensibly high that electrons are smashed into protons, merging to become neutrons. The outer layers of the star bounce off this newly formed hyperdense core and blast outward in a supernova explosion. What remains behind is a neutron star. The Crab Pulsar is a sphere roughly 20 kilometers across. That is a distance you could drive on a highway in 15 minutes. Yet, packed inside this tiny sphere is a mass equal to about 1.5 times our entire Sun. The density is so extreme that a single sugar cube-sized chunk of the Crab Pulsar would weigh as much as Mount Everest. But here's where the physics get truly bizarre. When the original star collapsed, it conserved its angular momentum, just like an ice skater pulling their arms in to spin faster. Because the star shrank from millions of kilometers across to just 20 kilometers, its rotation accelerated to absolute extremes. The Crab Pulsar spins on its axis 30 times a second. Its equator is moving at roughly 2,000 kilometers per second. But extreme density and mind-bending speed alone don't explain why the Crab Pulsar shines across the universe like a beacon. For that, we have to look at its invisible cage. As the star collapsed, its magnetic field was compressed along with it, amplifying its strength to terrifying levels. The magnetic field of the Crab Pulsar is roughly 2 trillion times stronger than Earth's. This magnetic field is so intense that it literally rips charged particles, mostly electrons and positrons, right off the solid surface of the neutron star. These particles are caught in the magnetic field lines and accelerated to nearly the speed of light. As they spiral outward, they emit a highly focused beam of radiation, ranging from radio waves to X-rays. Because the magnetic poles of the star are not perfectly aligned with its axis of rotation, these twin beams of radiation sweep across the cosmos like a lighthouse. Every 33 milliseconds, one of these beams sweeps past Earth, and our telescopes register a pulse. When pulsars were first discovered in 1967, astronomers didn't know what they were. Some even joked they might be signals from alien civilizations. But the discovery of the Crab Pulsar in 1968 changed everything. Because it sat exactly in the center of a known supernova remnant, it definitively proved that pulsars were the rapidly spinning neutron stars predicted by theoretical physics. For decades, we thought we understood the rules of this cosmic lighthouse. We had the math, we had the models. Until recently, when the Crab Pulsar decided to break our laws of particle physics entirely. When we look at the Crab Nebula through our standard telescopes, it's a visual feast. It looks like a shattered rainbow, woven from glowing filaments of hydrogen, oxygen, and sulfur. But if you possessed gamma-ray eyes, you would realize that these beautiful colors are just the tip of the iceberg. At the dead center of this shattered rainbow sits a cold blue-white dot, the Crab Pulsar, and it's conducting a relentless, insane cosmic bombardment. For a long time, scientists believed there was a strict physical speed limit to how much energy a pulsar could pump out. But when astronomers pointed the magic gamma-ray telescopes at this blue-white dot, they realized they were completely wrong. They detected pulsed signals reaching a staggering 1.5 Peta-electron volts. What does that actually mean? Imagine a regular photon of visible light, the kind hitting your eyes right now, as a tiny lightweight ping pong ball. By comparison, the high-energy photons being fired at us by the Crab Pulsar carry the kinetic energy of a massive bowling ball, slamming you at 100 kilometers per hour. According to our existing physics models, this simply shouldn't happen. Inside such a terrifyingly strong magnetic field, electrons should lose all their energy to extreme friction and radiation long before they can accelerate to these levels. But the Crab Pulsar does it anyway, and with terrifying ease. It's the cosmic equivalent of riding a rusty, beaten-up bicycle on a mountain road covered in speed bumps, and somehow hitting the speed of a supersonic fighter jet. And the bombardment doesn't stop there. Recently, China's Lasso Observatory captured something even more terrifying. Photons erupting from inside the nebula, packing an unbelievable 1.1 peta-electron volts, or PeV. That's 1 quadrillion electron volts. This discovery confirmed that the Crab Nebula is a true PeV-tron. This dead star, barely the size of a small city, is 1,000 times more efficient at accelerating particles than the Large Hadron Collider, the most powerful and expensive machine ever built by humanity. In 2024, the James Webb Space Telescope revealed the sheer, violent beauty of this extreme engine in unprecedented detail. JWST's data showed us that the pulsar winds blowing out from the star isn't just a gentle stream of radiation. It acts like millions of high-energy plasma cutters, physically slicing through and violently bulldozing the surrounding interstellar dust, driving the expansion of the entire nebula. We aren't just looking at light. We are watching an ongoing extreme physics experiment that is actively rewriting the rules of the quantum universe. It commands the space around it with absolute, terrifying authority. Yet the most violent events actually happen deep inside the pulsar itself. The Crab Pulsar is not a perpetual motion machine. Because it's powering this massive wind and sweeping its beams across the galaxy, it's constantly losing energy. It's slowly applying the brakes. Its rotation speed is decreasing by about 38 nanoseconds per day. But occasionally, the Crab Pulsar does something completely unexpected. It glitches. Without warning, the spinning star suddenly speeds up. How does a dying star spontaneously spin faster? The answer lies beneath its surface. The crust of the Crab Pulsar is a rigid lattice of iron-like nuclei, 1 billion times stronger than steel. But beneath this crust lies the core, which scientists believe is made of a neutron superfluid. A superfluid is a bizarre quantum state of matter that has exactly 0 friction. Inside this frictionless core, the fluid rotates by forming millions of microscopic quantum whirlpools called vortices. Many of these vortices become physically pinned to the solid inner crust of the star. As the star loses energy to space, the solid outer crust slows down, but the superfluid inside, having no friction, wants to keep spinning at the same speed. Tension builds. The difference between the solid crust and the liquid core reaches a breaking point. Suddenly, snap! Millions of quantum vortices unpin simultaneously, violently transferring their momentum to the crust. The entire star violently jerks, instantly spinning faster. This is a starquake. It's a microscopic quantum event happening on a macroscopic, city-sized scale. But these quantum hiccups are ultimately just the dying gasps of a dying engine. The Crab Pulsar is slowly bleeding its rotational energy into the cold void of space, which brings us to its ultimate fate. Right now, the Crab Pulsar is in its prime. It's young, energetic, and incredibly violent. The wind it generates is still pushing the debris of the supernova outward at thousands of kilometers per second. But this cannot last forever. Over the next few million years, the Crab Pulsar will continue to slow down. As its rotation drops, its once mighty magnetic field will lose the power to rip particles from its surface. The magnificent beams of radiation will begin to flicker, weaken, and eventually stop. The Crab Pulsar will cross what astrophysicists call the death line. When that happens, the glowing Crab Nebula will fade into the dark, dissipating into the interstellar medium. All that will be left is a cold, dark, silent sphere of neutrons, wandering the Milky Way, a ghost of the magnificent explosion that lit up Earth's skies in 1054. But for now, the Crab Pulsar continues to beat at the heart of its nebula, a 30 Hz metronome keeping time in the constellation of Taurus, reminding us of the extreme, terrifying, and beautiful physics that govern our universe.